Hello, in this video we'll be working through Unit 7 homework problems 47 through 51. For 47, we have region R bounded by the graphs of y equals ln x and the line y equals x minus 2. We want to find the volume of the solid whose base is region R formed by cross sections perpendicular to the x-axis that are semicircles. And then for part B, the same thing, but the cross sections perpendicular to the x-axis are squares. So for part A, our cross sections are perpendicular to the x-axis, and that means I am going to draw my reference rectangle perpendicular to the x-axis. And I'm looking at a top-down view, so I'm seeing the base of this solid. But if I imagine slicing it and then kind of looking at it from the side, looking at my slice from the side, it's going to look like it's in the shape of a semicircle, something like that. And so our basic setup, since this is a vertical slice, it's a dx problem. My volume for semicircles, our coefficient is pi over 8. So it'll be pi over 8. And then we integrate the length of that rectangle squared. So to figure out the length of the rectangle, this is vertical distance. We're going to do top minus bottom. In a dx problem, we want to know what this y is equal to. So the top function here, the yellow function, we've got y equals ln x. And the bottom of the rectangle is touching this purple function, which is y equals x minus 2. So I take the top y minus the bottom y. And that's going to be ln x minus x minus 2. So that's the length of the rectangle. We're going to square that times dx. So there's our setup for the volume when the cross-section is in the form of a semicircle. We can compute that on our calculator. I'm going to go ahead and enter the top function in y1, so ln x, the bottom function x minus 2 in y2, and then my volume is pi over 8. Let's try that again. Pi over 8, math 9 for my definite integral. Oh, I didn't write bounds. So this is a dx problem. We want to go from the x coordinate where our region begins to the x coordinate where it ends, and I have not found that yet. So let's go back. Let's back up. We've got ln x in y1, x minus 2 in y2. And let's just try zoom 4. We'll see how that's going to work. Yep, that works out just fine. And then I want to find my points of intersection. Let's bring my cursor in. Okay, so I have points of intersection at here x equals 0.1586. And then my other point of intersection (3.1462). Okay, so now let's try evaluating our integral once again. So we want pi over 8, and then math 9 will set up our integral from 0.1586 to 3.1462. And I want y1 minus y2 squared. So I need parentheses. I'm going into F4 to call up y1 minus y2 squared with respect to x. And we get 0.607. For part A. Now part B, it's almost the same setup, only our coefficient changes, because now we want our cross sections perpendicular to our x-axis to be in the shape of a square. So for this one, we just don't have the pi over 8 in front. The coefficient for squares is just a 1. Other than that, same integral. So 0.1586 to 3.1462, and then ln x minus the quantity x minus 2 squared dx. So I'm going to just hit second enter to call up my last thing that I did here, and I'm just going to delete the pi over 8 in front. And that gives me a volume of 1.545. Number 48, let f and g be functions given by f of x equals 1/4 plus sine pi x, and g of x equals 4 to the negative x. Let R be the region in the first quadrant enclosed by the y-axis and the graphs of f and g, and let S be the region in the first quadrant enclosed by the graphs of f and g as pictured below. Got a typo there. Part A, find the volume of the solid whose base is the cross-section area of region S and is formed by squares that are perpendicular to the x-axis. Okay, so I'm going to draw my reference rectangle perpendicular to the x-axis. I'm using region S as the base of the solid, and then those cross-sections are in the shape of squares. Okay, so if we can imagine a square coming up off the page there. It's got some thickness to it. So we're going to need to find our points of intersection like we did on the last problem. So we know our lower and upper limits of integration, but the basic setup is for my volume, it's a square, so the coefficient is 1, and then I just integrate. This is a dx problem. So from x equals, I need to find those x values. And then it's just going to be the height of that rectangle, which I find from the top y minus the bottom y. So the top y is, let's see, that would be the f of x is going to be the top y. So we'll call this one f. And the bottom is g. Okay, so I'm going to want f minus g squared dx. Let me enter these new equations. So my f of x, 0.25, plus the sine of pi times x. And then g of x is 4 to the power negative x. Okay, so we can do better with our window. Maybe x should go from 0 to 2, and y could also go from 0 to 2. That should be fine. Okay, so I need to get my points of intersection. It looks like that's at 1. Okay, 1 comma 1/4. And then on the left, we have a point of intersection at 0.178, comma 0.781. Okay, so we're integrating from 0.178 to 1. And my f of x equation is in y1, my g of x equation is in y2. So I'm going to use math 9, going from 0.178 to 1. y1, actually I want parentheses here. Let's try that again. Parentheses, and then y1 minus y2, all of that squared with respect to x. And we get 0.25, approximately 0.25. Now part B is asking us to find the volume of the solid whose base is the cross-section area of region S and is formed by equilateral triangles perpendicular to the x-axis. So the only thing that changes here is the coefficient. And I've already computed the integral, and I got about 0.25 for the square with the coefficient of 1. So really I can just take this answer and multiply it by the proper coefficient for, was it equilateral? Yes, equilateral triangle, which is square root of 3 over 4. So I'm going to multiply this answer by the square root of 3 over 4, and I get 0.108. So the answer to part B, 0.108. (49) Let f and g be the functions given by f of x equals 2x times 1 minus x, and g of x equals 3 times x minus 1 times the square root of x for x between 0 and 1. The graphs of f and g are shown in the figure below. So we're going to want to figure out which is which. F of x is a quadratic function, parabola opening down, so that must be the top function, f of x. And our bottom function then must be g of x. Find the volume of the solid whose base is the cross-section of the region bounded by the graphs of f and g and is formed by squares that are perpendicular to the x-axis. So here's my reference rectangle. And I like doing the square first because the square just has a coefficient of 1, and we can take that answer and just multiply it by whatever coefficient we need to get other shapes. Okay, so here's my square popping out. And my volume for the square, this is a dx problem. So I need to figure out my x values, which in this case are the x-intercepts. So I can get that just by looking at the equation for f of x. There's an x-intercept at 0 and there's an x-intercept at 1. So we're going to integrate from x equals 0 to x equals 1. And it's just going to be the top y minus the bottom y. So the top y is f. Let's do f minus g. We need to square that and then multiply by dx. Let me enter my functions. So 2x times 1 minus x, and then 3 times x minus 1 times square root x. And let's just verify we're looking at the right thing here. Need a better window. Y min, let's try -3. Okay, that looks right. And we are good to go. Math 9, from 0 to 1, f minus g squared, so that's y1 minus y2, squared with respect to x. And that gives me a volume of 1.493. Now for part B, it's the same setup, but now the shape is a semicircle. So all we have to do is take our answer 1.493, which was for the square cross-section, and multiply it by pi over 8. For part C, our shape is an equilateral triangle. So we just take the volume formed by square cross-sections and we multiply it by square root of 3 over 4. And then for part D, we have an isosceles right triangle with a hypotenuse on the base. So we take our 1.493 and we multiply it by 1/4. Okay, so those values, if we compute them, 0.586, 0.646, and 0.373. Number 50, let R be the region enclosed by the graph of f of x equals x to the power 4 minus 2.3x cubed plus 4, and the horizontal line y equals 4, as shown in the figure below. For part A, we want to find the volume of the solid generated when R is rotated about the horizontal line y equals negative 2. So y equals negative 2, we'll say, is right here. That's our axis of rotation. So here, keyword is rotated about. We know we're either doing dishwasher or shell method to find this volume. We're not doing cross sections here. It's rotated about y equals negative 2. So now I'm going to decide whether I want to do this as a dx problem or a dy problem. Right now, the equation given to me is in the form of y equals. So it's a function of y, or it's y equals a function of x. So I don't want to have to try and solve this for x. Looking at the equation, it looks too difficult to solve for x. So I want to do this as a dx problem, which means vertical rectangles. And that means washer method. So I have my outer radius. When you're doing washer method, your rectangle always touches your axis of rotation. So vertical, so it's a dx problem, and then I've got my empty space, or my inner radius, here. So my setup now, and I'm going to need to get these points of intersection. X to the power 4 minus 2.3 x to the power 3 plus 4 is equation 1, and then we had the horizontal line y equals 4. Okay, let me fix my window. I think maybe just the y's needed to be adjusted there. Let's try that. Nope. X max needs to be larger. We'll go with 5. Okay, so I need to get that point of intersection on the right. There we are. 2.3 comma 4. All right, so now our setup here, volume equals pi times the integral. This is a dx problem, so we're going from x equals 0 to x equals 2.3. And then we have our outer radius, which is a vertical distance. So we do the top y right here minus the bottom y right down here. So the top of the rectangle is touching y equals 4. Minus the bottom of the rectangle is touching y equals negative 2. 4 minus negative 2 is 4 plus 2. That's my outer radius squared. Squared. Let's try that again. Squared. Minus the inner radius. Okay, the top, this is vertical distance again, so I want the top y minus the bottom y. So the top y is touching my function f of x. I'm just going to call it f so I don't have to write that all out. And the bottom is touching negative 2, so f minus negative 2. That's my inner radius. So outer radius squared minus inner radius squared times dx. Which gives a volume of 98.868. For part B, region R is the base of a solid. And for this solid, each cross-section, so now I know this is not dishwasher or shell, this is a cross-section problem. And the cross-sections are perpendicular to the x-axis. So I have cross-sections perpendicular to the x-axis in the shape of an isosceles right triangle with a leg in R. So my coefficient is 1/2. My setup, volume equals 1/2. That's my coefficient for isosceles right triangle with a leg on the base. And then I'm integrating from x equals 0 to x equals 2.3. I got that from part A. And then we need the radius squared. I shouldn't call it a radius. The length of the rectangle we need squared, and then times dx. So it's vertical distance, so the top y minus the bottom y. The top y is touching 4. The bottom y is touching f of x. So this is 4 minus f of x, all of that squared. And that gives us a volume of 3.574. Part C, the vertical line x equals k divides R into two regions with equal areas. So I don't know where exactly it is. I'm just looking at it, and I'm going to estimate that it's about right there. Okay, so this is x equals k right there. Write but do not solve an equation involving integral expressions whose solution gives the value of k. Well, there's two different ways we can do this. We can find the area of that whole region R, divide it by 2, and then set up an integral and set it equal to that. Or we can divide this into two areas and integrate from 0 to k and then from k to 2.3 and set those equal to each other. So in other words, and this is just area, this isn't volume, this is just area. So the integral from 0 to 2.3, nope, that's the whole thing. I'm going to do it the other way. So I'm going to go from 0 to k, okay, and that area, we're going to do a vertical slice, making this dx. So we're going from x equals 0 to x equals k, and we're going to do the top y minus the bottom y. So 4 minus f. And it's just area, so nothing is squared, it's just multiplied by dx. Equals the integral if we start at k and end at 2.3 of the same setup, 4 minus f. Because if we draw a rectangle over here, it's also 4 minus f times dx. So that would be our setup there. And number 51, in the figure below, R is the region in the first quadrant bounded by the graph of y equals 4 ln 3 minus x, the horizontal line y equals 6, and the vertical line x equals 2. Find the area of region R. Okay, so we can decide if we want to do this as dx or dy. I'd rather do it as dx so I can do it with just one integral. If you were to try and do it as a dy problem, you'd have to split it right here and do it as two separate integrals. So if we're doing this as a dx problem, I'll draw a reference rectangle here. This is the area I'm looking for. And it's a dx problem, so I'm just integrating from x equals 0 to x equals 2. And top minus bottom, the top of the rectangle is touching y equals 6, and the bottom y is, well, it's not called f of x in this problem, so I guess I will just write it out. 4 ln 3 minus x. All of that times dx will give us our area, 6.817. Part B, find the volume of the solid generated when R is revolved about the horizontal line y equals 8. Okay, so I don't have a whole lot of room here for y equals 8, but I'm just going to draw it up here. That's my axis of rotation. And again, I'd rather do a dx problem so I don't have to do two separate integrals, and that would make this washer method. So I have outer radius and then inner radius. This is still my shaded region like it was in the previous part. So our setup for washer, we have pi, And then we're integrating from x equals 0 to x equals 2. The outer radius, this is vertical distance, so I take the top y minus the bottom y, which is 8 minus 4 ln 3 minus x squared. That's my outer radius squared. Minus, and now my inner radius, I do top y minus bottom y, that's 8 minus 6, or just 2, squared, times dx. And that gives 168.18. Part C, the region R is the base of a solid. For this solid, each cross-section perpendicular to the x-axis, so our reference rectangle looks like this, is a square. Okay, so now we have squares coming up off the page here. Find the volume of this solid. So for a square, our coefficient is 1, and then we integrate 0 to 2, just this distance here, this vertical distance, so top y minus bottom y. The top y is 6 minus the bottom y, which is 4 ln 3 minus x, squared, times dx. And that gives 26.267.